Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about correlation. The motivation is that when we're doing data analysis, it's often very important to determine whether there's a linear dependence between quantities of interest. So let's take a look at these three scatter plots that we have here. On the left, it's quite obvious that, I just occluded that it's B on the y-axis and A on the x-axis. It's quite clear that that B is kind of inversely proportional to A. So the two quantities are linearly related in that way. Here in the center, we don't really see any linear dependence. And on the right, we see that B is approximately linearly proportional to A. So our goal is going to be to quantify this linear dependence between quantities of interest, or equivalently between the random variables that represent our quantities of interest. The prerequisites for this material are multivariate distributions of random variables and averaging or expected value. Okay, so how can we quantify the linear dependence between two random variables A and B? What we're going to do is we're going to determine to what extent we can approximate B using a linear function of A. We're going to focus on standardized random variables that have zero mean and unit variance, but later on we will see how our results generalize to other random variables. Okay, so our goal is to find the best linear estimate alpha A of B given A. This alpha here is just a constant scaling factor that we're going to apply to A in order to approximate B. We're going to use mean squared error as our metric to determine how good this approximation is. As we have explained previously in the course, the mean squared error is a reasonable distance between random variables. Okay, so again, we have B minus this constant times A. We take the square. We want to minimize the expected value of that. The first thing we do is we expand the square inside the expectation, and then we apply linearity of expectation. When we do that, the constants come out. We express this expected value of the sum as the sum of the expected values. Of course, the random, everything that is random, which we usually represent with a tilde on top of the variable, stays inside. And now we remember, I feel that I put too many arrows here. Now we remember that we're concentrating on random variables that have zero mean and unit variance. Since they have zero mean, their variance is just equal to the mean square. Because remember that the variance is equal to the mean square minus the square of the mean, but here the square of the mean is just 0. So this is just going to be equal to the variance of B, which is 1 by assumption. And by the same argument, this is going to be also equal to 1. The mean squared of A is also going to be is also equal to 1. So we get an expression here, which is a quadratic function of alpha. The mean squared error of this linear approximation of B given A is this quadratic function of alpha. Let's analyze this quadratic function. In order to do that, we compute the derivatives. The first derivative is just 2 alpha minus 2 times this expected value of the product. And now we take the second derivative to see how the quadratic function is shaped. If the second derivative is negative, then we'll be out of luck because the quadratic will look like this. It won't have like a minimum in the middle. It will just go to infinity and minus infinity. If it's positive, it will look like this, which, maybe like that, which will be good news because then it will have a certain minimum that we can find by setting the first derivative to 0. And the second derivative, as you can see, is just equal to 2. So indeed, we're in this case where we can just find the minimum by setting the first derivative equal to 0. We do that, and we obtain that the optimal alpha is equal to this expected value of the product. This is what we're going to define as the correlation coefficient, which is represented by this letter rho, the correlation coefficient between A and B. It's the expected value of the product between A and B in the case of standardized random variables that have zero mean and unit variance. We will see the general case in a moment. But before that, let's go back to our 3 scatter plots, and what we're going to do for our 3 scatter plots is we're going to consider a decomposition of the original data points, which, or rather, not the original data points, but we're going to consider the approximation that we obtain for the vertical quantity, which was called B. We're going to decompose that into a linear estimate that is going to be the correlation coefficient, which corresponds to the expected value of the product between A and B, and that expected value, as we will see later on, is usually approximated by, as usual, averaging. We're going to decompose, again, that quantity between this linear estimate and the residual, which is just the error that we get when we try to approximate B using this linear function of A. Okay, so let's do that. When we do it for our left graph here, the graph that we had at the left, this is the linear approximation, and indeed we see that B is directly proportional in the sense that when we compute the linear approximation, that linear approximation has a positive slope, and then this is the residual. Okay? So in this case, the correlation coefficient is positive. That's why this line has positive slope, and it's equal to 0.95, in fact. In such cases where the correlation coefficient is positive, which means that the linear approximation looks like that, this line that corresponds to the linear approximation of B given A is going up. In those cases, we say that the quantities are positively correlated when the correlation coefficient is positive. In our center graph, we had suspected that maybe there wasn't that much of a linear relationship, and we were right. When we compute the correlation coefficient, it's equal to 0, which means that A and B are not linearly related. If we try to approximate B using A, then the best approximation is just to set this to 0, to just say, okay, B is 0, don't know what's going on, and the residual is exactly the same as the original data points. In those cases, when the correlation coefficient is 0, which means that there is no linear dependence at all, we say that A and B are uncorrelated. In the rightmost graph of our examples, we said that this kind of looks as if B is inversely proportional to A, and we were right. When we look at the slope of the linear approximation, it's negative. The correlation coefficient is negative. In those cases, we say that the random variables are negatively correlated. So they are linearly dependent, but there's this negative correlation because essentially one is inversely proportional to the other. Okay, so now let's move on to what happens if we have random variables that are not zero mean and or not unit variance. So we're going to consider two random variables A and B that have an arbitrary mean mu A, arbitrary mean mu B, and arbitrary variance sigma A squared and sigma B squared. What we do in this case is to quantify linear dependence after standardizing the random variables. So we subtract the mean and divide by the standard deviation, which is just an affine transformation of the original random variable, affine because we're subtracting a constant, okay, but otherwise we're just scaling by the standard deviation. And we do that for the two random variables, and then we consider what is the linear dependence between them, with the logic that since we're just subtracting by a constant, so we're just centering, and we're just scaling, if there's linear dependence between these standardized versions of the random variables, then there should be linear dependence between the original random variables. Okay, so before we proceed, it's important to establish that these guys indeed are standardized in the sense that they have zero mean and unit variance. And that just follows from linearity of expectation. Should have probably written it because so that you guys wouldn't have had to suffer through my handwriting, but basically here we are. Okay, so what is the expected value of this standardized random variable? By linearity of expectation is just the mean of A minus the mean of A divided by the standard deviation. Okay, because remember that the mean and the standard deviation here are just constants, they can come out of the expectation. Okay, so the mean minus the mean is just equal to 0. So these random variables are indeed zero mean, because we have subtracted the mean, the original mean. Okay, we have centered the random variables so that they're zero mean. And let's take a look at their standard deviation. If we consider the variance of S of A, then because S of A is zero mean, I have just shown you that it's zero mean, this is just equal to the mean squared. Okay, so I would just square it, we take expected value, and now the denominator can just come out of the expectation by linearity of expectation, and we have that this is equal to the expected value of A minus its mean squared divided by its variance. But what is this? It's just its variance, by definition of variance, right? So this is indeed unit variance. So standardization of random variables is centering and normalizing so that they have zero mean and unit variance. Now we're going to define the correlation coefficient as the correlation coefficient between the standardized versions of these random variables. And we'll see that this makes a lot of sense. But first, let's take a look at what this definition amounts to in terms of the random variables A and B. So we say that the correlation coefficient between A and B is the correlation coefficient between the standardized versions of A and B. So the expected value of this product, we expand the definition of the standardized random variables, and what we obtain, once we apply here linearity of expectation to take the denominators out, is this expression where we have the standard deviations in the denominator, and in the numerator we have the expected value of the centered random variables. This expected value of the centered random variables is called the covariance between A and B. And intuitively, it's kind of the average joint fluctuations of A and B. Okay, so we center the two random variables just like we center when we compute the variance, and we multiply them together and take that expected value. Okay, this is called the covariance between A and B. Usually, we don't compute it in this way. It's a bit like the variance. Remember that the variance is really equal to the expected value of a random variable minus its mean squared, but when we go and compute it, we just compute the mean squared minus the square of the mean, because that's just easier to compute. So here this is a little bit similar. If we expand this out, we get that this is equal to the expected value of this product minus these cross terms. But in these cross terms, you have to remember that the mean of A is just mu A and the mean of B is just mu B. So we obtain this expression that is usually kind of easier to work with, which is the expected value of AB minus the product of the expected values. Okay, so in general, when you see the definition of correlation coefficient, it will often be expressed as the covariance divided by the standard deviations. The reason why we defined it in this other way is because I feel that this reveals immediately that it's connected with the linear dependence between the two random variables. So I feel that it's a little bit more of a natural definition when you look at the standardized random variables and you realize that the correlation coefficient is just this linear scaling that you have to apply to one in order to approximate the other one. But this is the more common definition that you will find in textbooks and online. Okay, so realize here that because these guys are going to be non-negative, when the covariance is positive, the correlation coefficient is positive. When the covariance is negative, then the correlation coefficient is negative. Okay, and if the covariance is zero, the correlation coefficient is zero, except if one of these guys is zero. But if one of those guys is zero, if the standard deviation is zero for either of the two random variables, then that random variable is just a constant. Okay, so this is not very interesting anyways. Everything is going to be zero because it's just going to be equal to its mean with probability 1. Remember that when the variance of the random variable is zero, then it's just equal to its mean with probability 1. It's not an interesting random variable. Okay, so assuming that that doesn't happen, when the covariance is positive, the correlation coefficient is positive. When the covariance is negative, the correlation coefficient is negative. When the covariance is zero, the correlation coefficient is zero. Okay, so when we see that the covariance between two random variables is positive, we might immediately say that they're positively correlated. If it's zero, we say that they're uncorrelated, and if it's negative, we say that they're negatively correlated. Okay, so how do we estimate correlation from data? How do we estimate the covariance and the correlation coefficient from data? So we're interested in two quantities. one of the quantities is going to be x, the other quantity is going to be y, and we have to have pairs, right? This only makes sense if we have pairs of points, because we want to see the joint behavior of the random variables. We already know, again, and to simplify notation, we're going to gather the first entry of each of these pairs into a set X, and the second entry into a set Y. All right, so if we already know how to compute the sample mean of each of these entries, right? We just sum everything up and divide by n. We already know how to compute the sample variance. We just add everything up and divide by n, or we can divide by n minus 1 if we want the estimate to be unbiased. It doesn't really matter very much. Now if we want to approximate the covariance is the expected value of the product of the centered random variables. So we can center xi and yi by subtracting their sample means, and then we can just sum these products and divide by n. Okay, that's the sample covariance. Now, if we want an approximation of the correlation coefficient, we just take that sample covariance and divide by our approximation of the standard deviations obtained from the sample variances. Okay, so now we're going to take a look at some examples. Here I'm using some real data from the NBA. So in case you don't know anything about basketball, we're going to be interested in the relationship between height and different offensive statistics. So different numbers that quantify how well a player is doing. A rebound happens when someone shoots, the ball comes out and you grab it. If you grab it, then you've gotten a rebound, and getting a lot of rebounds is important. So now we're going to see what the relationship between height and rebounds is. So think about it for a moment. You think they will be positively correlated. So that means that taller players get more rebounds. Negatively correlated, shorter players get more rebounds, or there's no relationship. Well, the answer is kind of clear when we look at the scatter plot of points. Indeed, taller players seem to get more rebounds, and when we compute, and this is just because I wanted to put the KD, the kernel density estimate, so an approximation of the PDF between these quantities, because you can't really see the density of points here. There's many more players here that don't grab that many rebounds, because there are more players that don't do that well than players that do very well. And that is not completely apparent in the scatter plot, so that's why I wanted to show you the KD, so you can see that the density is higher here, the density of players. But anyway, so this is the density, and now we're going, and it does seem indeed that it's increasing, like the number of rebounds increase with height, which, by the way, again, if you've never played basketball, this actually makes a lot of sense, because the players that are usually responsible for grabbing rebounds are the taller players, the centers or the power forwards. So it turns out that the correlation coefficient that we compute directly from the data is 0.42, which indicates that there is this linear dependence, and that it's proportional. Basically, the taller players are, the more rebounds they get. Okay, so this is the standardized. This is what happens after we standardize the scatter plot, dividing by subtracting the means and dividing by the standard deviations that we compute from the data. This is the linear estimate. So the slope of this linear estimate is the correlation coefficient, which is equal to 0.42, and this is the residual. Okay. So again, this indicates that there is a linear dependence between the two quantities. Let's do the same for assists. An assist is basically when you pass the ball to someone and that someone scores. Again, try to think for yourself if you think that height and assists are going to be, whether they're going to be linearly dependent, and if so, will taller players get more assists or shorter players get more assists? This is the scatter plot, and it seems from the scatter plot that shorter players get more assists. Let's take a look again at the density estimate, because again, there's a higher density of players down here in the scatter plot, and that's not immediately obvious if you just look at the points. And it does seem again that the shorter players get more assists. if you haven't seen a lot of basketball, this is natural because the point guards, who are the shortest players, are usually the ones responsible for passing the ball around. Although there are some notable exceptions. In particular, now Nikola Jokic is an incredible passer, and he's really, really tall. But I don't want to get carried away, so I'll stop talking about that. When we compute the correlation coefficient from the data, we see that indeed it's negative. So height and assists are negatively correlated. We're going to look at the standardized density here. This is the linear approximation, so we see this inverse proportional in the relations of this relationship of inverse proportionality, and this is the residual. And now finally, height and points. If you had asked me before looking at the data whether there was a correlation between height and points, to be honest, I wouldn't have known what to say. Because there are tall players that score a lot, there are short players that score a lot. I wouldn't have known what to say. As it turns out, when you look at the scatter plot, it's difficult to say. Also, if you just look at it, this is the density of players. When you compute the correlation coefficient, you realize that there is a small linear dependence, which is negative, interestingly. So this is a little bit clearer if we look at the standardized variables. When we look at the approximation and the residual, we see that this indicates that there is, a slight negative correlation between height and points. It seems that shorter players on average score a little bit more than taller players. Okay, so now we're going to talk about Gaussian random variables. You might not remember. You can take a look at the corresponding video, but when we talked about Gaussian random vectors, we had looked at this example where we looked at a Gaussian vector that had a zero mean and this covariance matrix. So you will probably realize that we have used the word covariance before here, but remember that when we're talking about the covariance matrix of random vectors, we'll see that actually they correspond to the covariance matrix of the corresponding random vector, but we had just thought about it as a parameter. So for now, let's continue that way. Let's just think of this as a parameter. We had taken a look at what happened when the covariance matrix looked like this, which meant that the variances of the individual random variables of A and B were equal to 1. I don't know what I was thinking there. They're equal to 1. And then we had this parameter in the off diagonal, which was rho. Now maybe you will understand why I chose rho to represent this parameter. What we had seen is that when we changed this parameter, we changed the conditional distribution of A given B or of B given A. And this is what the contour plots look like when we change the parameter rho. This is what happens when rho is equal to minus 0.75. This is what happens when rho is equal to 0. And this is what happens when rho is equal to 0.95. So now we're going to connect this to the correlation coefficient that we have defined previously. So we had determined by essentially writing out the joint distribution of these two random variables for those particular values of the parameters, so mean 0 and this covariance and this covariance. We had determined that the conditional distribution of B given a specific value depended on rho and that specific value. So the mean was equal to rho times A and the standard deviation was equal to 1 minus rho squared. So now we're going to compute the correlation coefficient of these random variables using this information. And this is also going to be a nice example of how to use iterated expectation to make complicated calculations in pretty easy, if you have access to conditional distributions. Okay, so we want to determine what is the correlation coefficient between A and B, where A and B are form a Gaussian random vector with zero mean and this covariance matrix. So we want the expected value of A and B because, again, here we already see that these guys have unit variance and zero mean, right? So they're standardized random variables. We just need to compute the expected value of their product. Okay, so we're interested in the expected value of their product. We can apply iterated expectation because we know the conditional distribution of B given A. Okay, and And that means that we can compute this, to be clear, as a B conditioned on A, and then we take another expected value, okay? That's iterated expectation. But this object here is always a little bit kind of tricky to manipulate, so let's do it in 2 steps. We take a look at the conditional expectation given a fixed value of A. Given a fixed value of A, this guy is just equal to A, and we have seen that B given A, the mean of that is just rho A. Okay, and again, like this result that the conditional mean is equal to rho A, we obtained it by essentially writing out the distribution. You can take a look at the video on Gaussian random vectors to see how we did that. But the important thing is, for now, is that we have this expression of the expected value of A times B given this fixed value for A. Now, if we want the expected value of A times B in general, we just need to basically plug A in again here. And this is the weird thing that we do when we define the conditional mean, because remember that the conditional mean is a random variable, which is a little bit strange. You can go back to the video on conditional expectation to review that if this still sounds a little bit weird. But the thing is that we showed that the expected value of A times B is just the expected value of this conditional expectation when we plug A back in. If we plug A back in into this expression, this is just equal to E times rho times A squared, where I have forgotten that this is still squiggly A, this is still a random variable. Now rho can come out, again this is a random variable, and we know that this guy has unit variance. So, this is my punishment for having that small typo, we see that rho is actually the correlation coefficient of these 2 Gaussian random variables. So that's why it determines now we understand. I'll go back just a bit to these plots that we had here. Now we understand why when rho is negative, the distribution is shaped, the ellipse that determines the ellipse that corresponds to the contour lines, of the Gaussian density seem to indicate a relationship of negative proportionality. When rho is equal to 0, this is just spherical essentially, and where rho is positive, there is direct proportionality. Okay, so it's kind of satisfying that we can connect this parameter rho to the correlation coefficient of the 2 random variables. And it also allowed us to review iterated expectation. Okay, so what have we learned? We have defined correlation, which allows us to quantify the linear dependence between random variables. Thank you very much.